Welcome to Code Club. You can think of it a bit like CSI, but for code. So I'm here with my crack team of hand-picked forensic code investigators here in the basement lab at the Bitfield Institute of Technology, which, by the way, is a fully non-accredited institution. So I'm here with Rakesh and Adebayo, and we're going to look at some Go code, and we're going to just see what we can figure out about it. So it's not so much a whodunit. We know who done it. In fact, it's Melina, one of my mentees. It's more of a why done it, if you like. So we'll see if we can figure out why this code. So to introduce you to this package, this is a link checker for websites. I asked Melina to do this partly because she was an excellent engineer looking for a Go project, and partly because I needed to check my website for broken links. Because, you know, there's quite a lot of material on bitfieldconsulting.com now. I've got all my Go tutorials, I've got my bookstore on there, I've got various blog posts. And you know how the web is, people are always changing their URLs or taking down websites or whatever. So I don't want any broken links on there, just looks bad. So what I want is a program which will basically crawl my website, find every page, check all the links on there, and any links to outside websites, you know. I mean, I want to know about broken internal links as well, but I'm primarily concerned with external ones, and I want to know about them. And of course, because Melina is an awesome Go programmer, she did this concurrently, because we're using Go, right? So we have concurrency, it's built in. Why not be concurrent if you can? And this is an inherently concurrent problem, isn't it?
Yeah, true. The faster you could solve.
Because if you think about it, you know, a link checker is going to spend most of its time waiting for you to do HTTP requests. Why not use that time to make more HTTP requests? Let's completely saturate our outbound bandwidth if we can. Why not? And saturate all my CPUs. I paid for a lot of expensive Apple CPUs. I don't want them sitting there idle. They won't be earning their keep. So that's why concurrent. So would anyone like to start us off just by reading through this? Maybe, should we tackle the tests first or the code first? It's up to you.
We can tackle the tests first, but I have never done any code on weight groups.
Right, sounds like you just volunteered though. Well done. Good man. Why don't you help us read through one of these tests and we'll see if we can figure it out together.
Yeah, sure. So this test package, this first function appears to be crawling across to find the broken links. So that's why she named it as test crawl broken link. And then we have this line number 14 called t.parallel. I assume that all the test cases runs in parallel.
Yeah. Again, when I'm running my tests, I don't want to have CPUs sitting around idle. I want to be using them. If I have 8 CPUs, I want to run 8 tests at once.
Yeah.
Nice side effect of that, by the way, is if there's any concurrency bugs in your program, you'll find them pretty quick this way, won't you?
Oh, I see. So is it like a race condition?
Yeah, exactly. So if you have any global data, for example, which Bukola and I were discussing yesterday in Let's Code, that could cause concurrency issues if people are trying to use multiple instances of your link checker. Maybe you want to check 10 websites, you know, and you kick off the link checker and you want each of them to be managing their work independently. As soon as you try and run tests in parallel, by calling t.parallel, you'll immediately find those kind of bugs because your program will crash. Ask me how I know.
After a disaster.
Yeah, all concurrent programs have tons of bugs, as anybody will know who's ever written one. It's not Go's fault. Go arguably makes concurrency easier than most languages, but concurrent programming is hard in general. We've only got one brain each, most of us, so it's hard for us to think about multiple computations going on concurrently, but nonetheless, Go can do it. So yeah, T-parallel, go on.
T-parallel. And then next, there's a Boolean variable called. I assume that this variable will be used to check whether a endpoint has been called or not down the line.
Yeah, that sounds believable, doesn't it? We may find out more about that later on.
Next, a new TLS server method is called on HTTP test, and to it, we are passing a HTTP handler and setting called is equal to true. I don't know what exactly it does here. Is it like a setting of HTTP server?
Yeah, anybody seen this kind of code before? I know some of you have.
I have seen part of it, like where we define the HTTP server, that HTTP.handler func, and then passing a response writer and request.
Yeah. Anybody would like to speculate about why we have a TLS server here?
Because it's an encrypted connection.
Tiago is right. Yeah, it's encrypted, and we definitely always want to be doing TLS, because if we're doing HTTP, we need TLS. We're not animals. But that's why new TLS server. But why do we have an HTTP server at all? Is the question really?
Sorry, I didn't get the question.
So we're testing an HTTP client in effect, aren't we?
Yep.
The link checker will be making HTTP requests. So in order to test it, we don't want it really calling out to the network. That would firstly annoy people on the network, and secondly, it would be quite slow. So we want to really do HTTP requests, but we want to do them locally. So one nice way to do that in tests is to use the HTTP test package. Will give you a little local TLS server that you can talk to, and you just give it a handler func, which, if you haven't seen one of these before, essentially when the server receives your request, you will be here. So you will enter this function. You will have the HTTP request that's being made as your parameter, so you can read things from it like, what's the URL? What's the HTTP method? And you need some way to talk back to the person making the request. So here's the response writer that we can write to. We can write HTTP headers, for example, like status not found. So this is really kind of a nice little pattern, and it's just, you know, very convenient to set up little fake servers to talk to. So that's what we're doing here. So can we work out what this fake server does when it's called?
It's always sending status not found.
Anything else?
So I really don't understand this called Boolean, why it's required, because you already have the TS, which is the response of your request.
Good. I'm glad you don't understand it, because if we all understood this, then we'd be kind of wasting our time, or spending it in a pleasant way, perhaps, but it wouldn't be quite as good a learning experience. So thank you for bravely confessing that. So can we try and answer that question? What is this called business about, for example?
The only thing I can, because this is a test I'm looking at, right?
Yep.
The only thing I can think of is that meant to be our testing variable? Is that why?
But if you pass the block, like why it wouldn't be executed?
Sorry, why wouldn't?
Like as I understood, it's a variable, and you check if it's true. Otherwise, you're going to fail your test.
Yeah.
But why it wouldn't be called? That's my question. Why
Why that
these?
wouldn't run?
Yeah.
Good question.
Yeah, well, let me tell you why we put this in. Was because we first of all wrote this, and of course, because we work test first, we wrote the test. We said they need a fake HTTP server. The name of this test is telling us we want to test what happens when the link is not found, which is what we're looking for. So we've got a fake server that returns not found, 404, and we ran the test and it passed. But we thought, hang on, we haven't written the bit that makes the HTTP request yet. So why is it passing? And the point is, of course, that this server was just ignored. It was never called, and then we got to the end of the test, so we passed. So we realized we need some way to know, did it actually make the request? And one way to do that is to say, here's a bool variable. Because we declared it with var, it gets its default value, which for bool is false. So if we don't do anything else, called will be false when we get to here, and we'll say, uh-oh, you didn't actually do the thing. So here's the other thing that the fake server handler does, is it sets called to true. That's how we know that we visited this piece of code, in effect. Does that make sense?
Yeah, I got the idea, but I don't see why you need that.
Yeah, he said he doesn't. You mean you don't see why that TS line of code from 16 won't run, is it? So I know that was the question he asked before, and it got me thinking as well, that is there any reason why that won't run?
Yeah, so what do we have here really? We have here a function literal, which some of you have seen. So we could have just defined this as a regular old func somewhere else in the code, and then we could just call it. But it doesn't need a name because we're passing it to TLS server and we're saying, hey, whatever request you get, just call this function. I think maybe JavaScript programmers might call this a callback or something like that, wouldn't they? I don't know.
Yeah.
I haven't been to the Bitfield Institute of JavaScript. So you tell me.
You probably don't want to set one up.
You can run that one.
No, thanks.
So this is not, if we mention the function literal, that's not the same as executing it. We're just saying here's a chunk of code which you may decide to run later on at your leisure. We're passing it to TLS server and we're saying, don't run this now, but when you get an HTTP request, here's the thing to run. Here's the handler for it.
Got it. Okay, got it.
Okay, should we go on?
Yeah, because you don't have the parentheses in the end, right? So it's not executing that.
Right.
Okay. Yeah, gotcha. Thanks.
It's a bit like a deferred func. If you've seen one of those, you can say defer func something something something, and it doesn't actually execute that func until later, specifically when you exit the function, or in this case when you get an HTTP request.
Gotcha.
So I'm not a big fan of mocking, but I guess we kind of mocked the internet here, right? So there's an internet where every web page is 404, if you like.
Now, the next call would be a defer ts.close, which I would assume that the server connection gets closed by the time this test ends, which gets executed at the end of the test case.
That's right. I just gave away what defer does, didn't I?
Yeah.
But you knew anyway.
And we have an array of string expecting what we want. We are expecting a structure called URL comes inside the want. So a list of URLs which we would expect. Next, we said links.newChecker. I was wondering what is this links here? Is it an links is imported as a package. So I assume that it's called from links.go.
Mm-hmm.
Yeah. So in links.go, there is a function called newChecker, which has been called, and it's returning something.
Yeah, this is work in progress, by the way. So not all the doc comments are done. So if you're wondering how a BIT graduate could get away with not writing comprehensive documentation for their Go project, that's how. She's still working on it.
Now this newChecker, shall we go and see what the newChecker does, or shall we go run through the rest of the test cases?
Just as you like, but one question that might occur is why do we need this checker, whatever it is? Why do we need that? Why not just start checking stuff? Anyone? Bukola knows.
Not sure I do.
Because viewers of our smash hit spin-off series, Let's Code, where we're building a lunar lander, they will know that there is some state to a lunar lander. It has a position in space, velocity, and so forth. And so you need somewhere to store that. And of course, you could just stick it in global variables in the package. But we're not going to do that because we're decent folks. And we don't, we don't pollute the global namespace like that. We also don't want concurrency bugs, especially because this is a concurrent program. We haven't concurrentized the lunar lander yet, have we? But we could do.
Yeah. So here, this newChecker is returning, I assume, certain things. One of that is HTTP client.
Yeah.
Is it there in line 25 here? Is it an assignment or comparison? Is that c.http client is equal to ts.client?
That's a struct field, yeah. So that's giving us another clue, isn't it? So you know, first of all, the checker has some state in that it'll have a bunch of worker Go routines which are fetching web pages and checking them. So that state needs to live somewhere, and you only have two choices. Either it can live globally, in which case you can't use this package concurrently, and people will be angry with you, or you put it on some kind of object, and the object basically exists purely to store that state. And we'll see that when we look at the package. But here's the other thing. Here's the other reason why we need that checker object so that we can put an HTTP client on it. Anyone know why we have to do that?
No, I don't know.
Feel free to speculate. It's a safe space here. And what's said at Code Club stays at Code Club. And to a rather limited audience on YouTube.
So we're kind of setting a HTTP client there with whatever from the client what we created server from. assuming that new checker doesn't return HTTP client, we are setting a HTTP client, what we have received from the server, the fake server we created.
Yeah, that's right.
But not sure why though.
Maybe it's related to concurrency, and when you have like more people calling or doing parallel calling, you have a different client for each call.
Yep, totally reasonable suggestion. There's more to it though. What would happen if we didn't do that and we just started trying to make requests to this TLS server? What do you think would happen?
I think nothing.
If you've ever tried to test an HTTP client in this sort of way, this is probably the first problem you ran into, in that the test TLS server serves a self-signed TLS certificate. Now, why would that be a problem?
Because it's not the library is not going to accept by default.
Yeah, absolutely. We don't trust self-signed TLS certs because it effectively completely bypasses TLS, right? It's just saying, hey, you know, I'm whoever I claim to be, and as proof of that, here's my signature. Well, great. That's very convincing. But it's fine for tests, of course. But if we use the default HTTP client out of the HTTP package to try and talk to a server like that, even a real server on the internet, it'll just say, nope, sorry, not going to do that unless you disable TLS checking, which you should never do. Otherwise, you're wasting a lot of CPU cycles on TLS if you're just going to bypass it. So what we need is an HTTP client that trusts that self-signed certificate, isn't it?
But where are we saying that my client accepts self-signed like certificate?
Well, what we could do is we could construct our own HTTP client. We could use HTTP client object from the standard library, and we could set on it, I think you set an HTTP transport which can accept a pool of CA certs or trusted root certs, for example, and we could get that cert and we could give it to the client and say, trust this. But that's a lot of paperwork, and luckily the TLS server itself will do that for us. So if we call client, it will just give us a client which trusts whatever certificate the server has. So that's super cool, because it means we have the working TLS server, which we didn't have to construct a cert for, and we also have a client that will talk to it.
I just understood a lot of code in the provider that I was not sure why it was there.
Right.
Thank you.
So that's very neat, isn't it? And you will see this pattern a lot anytime we're making HTTP calls. We'll probably do something like this.
Is this a test package, HTTP test?
Yeah, exactly right. So this contains lots of useful and cool things for testing HTTP clients and servers. But this is the one that I use the most, is the TLS server. You could perfectly well run your own real TLS server if you like. Not that this isn't the real one, but it's specially configured for testing. But you could perfectly well start one, but you don't really want to have to write a bunch of machinery, because we just need something that responds with 404. And that's really nice and easy to do.
That's it.
So now we know what that's about. So here's where we get to the stuff, isn't it?
Yeah. So now we are calling this crawl page method on the C, which is written by new checker, and we are passing ts.url. So this ts.url, not sure where it is being set. It's at a static? Is it like a read from an list from somewhere? I don't see another file supporting the ts.url, but we are passing an URL to the crawl pages.
I'll turn that over to the panel. Anyone know?
I think it doesn't matter, to be honest, because you are going to return just a 404, but I don't know if you are, it's mandatory to put, I don't know, a local host or something. But since it's a fake, it's a fake server, I think there is no URL because it's not going to check any file or anything.
Yeah, well, I'm calling it a fake server, but it is a real server, of course, but just a local one. But the point is, you know, we never at any stage told the server what its URL is. I mean, we're guessing it's going to be 127.0.0.1, some port, but we don't know exactly what. And fortunately, we don't need to know because the server itself, again, will tell us.
Yeah, that's what.
So the TS object will give you its URL and says, hey, just call me here, you know.
And test itself, it says we are testing for a broken link, so URL doesn't need to be the right one.
Well, we need to give it some URL to hit.
Mm.
If you think about it, you know, once the link checker has started crawling a site, it will itself generate a bunch of new URLs, all of the links that it finds. But it needs one to start with. It needs to know where the website is, and here's where it is. So when we're calling that code for real, if you like, from the CLI tool, we would give it bitfieldconsulting.com, for example. Other websites are available, but just not as good.
And now I noticed that my comment about doesn't send it, it's no sense because since you are simulating an ATP server, you need to follow the protocol. So you must specify the URL.
Yeah, that's right. We want it to be as realistic as possible. Otherwise, you know, you can end up faking so much stuff that you're actually not really testing anything, except maybe the equals operator. So yeah, so we're setting up a real server, calling it with a real client that trusts that TLS server, giving it the URL of the server, and crawl page. What do we think is going to happen here? Because we know this program is concurrent, therefore asynchronous. So how do we know when it's done, for example?
There is something called async wait group, but not sure how it returns.
Right, this is usually problem number one with concurrent programs, isn't it? How the heck do you know when it's done? Because you'll have Go routines running all over the place, and you've got no way of communicating with them unless you set one up. Yeah. So this is kind of suggesting that when crawl page returns, we're done, isn't it?
Yeah, that was going to say maybe it's handling the functions or it's handling itself.
Yeah. So we're saying if you kick off a call to crawl page, it will go and crawl the entire site, or as many, you know, it'll keep on following links as far as it can. Now there must be some boundary condition on that, mustn't there? Otherwise it'll end up spidering the whole internet, which could take a while. I don't want to be waiting for my tests while it crawls the whole internet. So what do you think the boundary condition might be?
Assuming at least one link is broken. If at least one.
That's possible, but then it might tell me, yes, you have a broken link on page X, and I go and fix it, and I run it again. So now you have a broken link on page Y. So I'd rather give me the whole list of links at once, and then I can go fix them all.
Maybe how much depth, John? Maybe go 4 or 5 depth or something like that.
Yeah, that's not a crazy idea, is it? But we could think of sites where that would result in us not actually crawling the whole site, just because there are so many, You know, think of things with category pages and 4 levels of categories or something. You know, by the time you've got down to the product page, you've actually run out of depth.
Or maybe everything on the specific domain. Are we checking something like that? Okay, as long as I'm on this domain, just go that my own domain, bitfield.com or something like that.
Yeah, I think that sounds better, doesn't it?
Yes.
In that,
not sure.
we know what domain we're on because it's in the starting URL. So we could say, of course, we want to follow links to outside domains because they're the ones we're chiefly interested in knowing whether they're broken or not. But if they're not broken, we don't really go any further, do we? Like if I link to golang.org, which I do, that's fine. Check that link, but don't then go to golang.org and start fetching all the links from there, because if there are links broken on that site, that's their problem. Don't come to me with it. So yeah, that happens to be exactly how it works. So what we're saying is crawl page will follow as many links as it can up to 1 level of links to outside domains and then come back. We assume that's a finite process. It might not be. You could have link cycles, for example, couldn't you?
Yeah.
And I don't think this code handles that yet, but we'll take a look in a second.
I have another question. Since you mentioned about waiting until all the Go routines are finished, not sure how to know that whether all the Go routines are finished or not. Let's say, for example, if there is a function which kicks off 10 Go routines and they just go and work behind the screens. For example, an event, like we are sending 10 events to 10 systems on a purchase of something.
Yeah.
And then if we are testing that function, and how do we test that function that all the Go routines have written or finished?
Yeah, that really is a genuinely excellent question. And can I postpone answering it until we look at the code where that happens? We might find out actually from looking at that. But you're right, that absolutely is the most important question. So, but we assume that crawl page somehow knows that it's done.
Yeah.
Now it comes back to us. So what do we do?
Now it comes back to us. Now, assuming that c.broken links will have all the links which are broken, if they are, and then we are mapping them into a variable called got. And then later, I assume that we're going to use this to check against what we want them.
Yeah, that's right. And broken links is quite a good name, isn't it? Because again, Melina is an excellent engineer, so she knows that probably 90% of software engineering is just figuring out the right names for things. And Bukola made this point yesterday as well, that this is the #1 hard problem in computer science, is naming things. The #2 problem is cache invalidation, but we won't be dealing with that today.
The next one is, I think she's checking whether the server is being called at all as well before even comparing the results what we have received from the checker.
Yeah.
Using the Boolean variable where we set true if the server is called.
Yeah, absolutely, because otherwise it would be possible for this test to pass without the code ever making HTTP requests, wouldn't it? It could simply set broken links to be whatever is expected.
Now here I have a question where, let's say here you said the tests are going to run in parallel. So the called, when it is set to true, does the new TLS server issues new server for each test case? Or is it going to be the same? Like if it is going to be the same, then if one server is called is set as true, then how about the other servers?
Yeah, really good point. So this is, again, one of the top 500 problems you have when writing concurrent programs is, if you're testing them, do you start one concurrent server for all your tests, and then you call it from each of your tests, and then you need to handle that concurrency? Then you have a problem, because tests by their nature want to call something and then they want to check what happened to the state of the world, right? So we look at the world beforehand, we do the thing, and then we look at the world again and say, did anything change? Because if not, this has been a huge waste of time. And in order to do that, we kind of need to know, did anybody else change the world while we weren't looking? And in a concurrent program, that's exactly what's happening, isn't it?
Yeah.
So, but I've had this problem in many a program, and several of my mentees have had this as well, that, you know, their tests become flaky because sometimes they work because the other parallel test didn't happen to modify that thing at just the wrong moment. And sometimes they fail because it did. So you've got two choices, basically, or two main strategies for dealing with this, I would say. One is have each test, you know, either you need complete control of the world or you need to give up all control. So if you have complete control of the world, you can say, yeah, I'm just going to start my own server. So I know its state, I know the state of this because I set it up. So I don't have to worry about anybody else messing with my world because it's a private world. Or you say, okay, it's a public world and lots of stuff is going to be going on. So therefore I can no longer make any assumptions about what's happening. So I maybe have to, you know, think about something where we each have our own checker, for example. So that's okay. We control that state. Other tests will create their own checker. So we don't have to worry about someone else writing something to broken links that we didn't expect. So did that long, rambling, discursive answer help you in any way?
Yeah, it makes sense. When we're running in parallel test cases, how do you maintain this parallel servers? Cool. Now the last part of the whole test case is to check whether what we have received from the broken links is matching to what we want here.
Yeah, I think
here she's using something called CMP. I think it's one of the package maybe imported, comparing against want and get. And if they're not matched, we are throwing a fatal error with the differences between those two. So it's nice and easy to read what the differences are.
That's right. So this is definitely a BIT house style thing, is that we could have, if we wanted to compare want and got, we could use go, of course. But because we want to compare slices, that's not as simple as equals. Because, you know, you might think if you have two slices, you can say, does A equals B? And it will tell you, but that doesn't quite work because a slice is a reference type, if you like, which is referring to some underlying array. And of course, they represent different arrays, even if they have the same contents. So it's like 2 copies of my best-selling For the Love of Go Fundamentals book, now available. They have the same text, but they're not the same object. One person might have written helpful comments in the margin, for example, or just insulting commentary. So same with slices. You know, they could have exactly, their underlying arrays could contain exactly the same elements, but nonetheless, to go, they're not the same object. So equals wouldn't work. What we'd have to do is really boringly, we'd have to loop over both slices. We'd have to loop over one slice, comparing each of its elements to the corresponding element in the other slice. And we're all busy people. None of us has got time for that kind of thing. So that's where the super useful CMP library comes in from our friends at Google. You can call cmp.equal and you can give it literally any 2 objects, any 2 variables of whatever type, and it will compare them. You could imagine these could be structs, which contain structs, which contain structs, and it will go through all of those recursively, comparing them deeply. And if they're not equal, which is the situation we're interested in the test, we want to say that, but we'd also like to know in what way are they not equal. So you can imagine if you had 2 slices of, let's say, 150 strings, maybe they're very nearly identical except for element 137, which has 1 character different. Now, what would you do in regular Go? You just say want X, got Y, right? You print out both slices. Imagine trying to read those and saying, ah, Go is telling me they are different, but they look super similar by eye. Very, very hard to see things like that in big slices or maps or even big structs. So what we would like is something that says, oh yeah, you know, all of these elements were identical, so I'll keep quiet about those. I'm just going to tell you about the ones that are different. And in fact, we would like a visual diff, like you get from the diff command, or from the git diff command. We would like to say, here's the line I expected, and here's the line I actually got. And that's what comp diff will do. So if you ever look at any of my projects or any of my mentees' projects, they all end with these 3 lines. Every test ends the same way. Saves typing because we can just copy and paste it. So that was excellent, thank you. I think we've got a good sense of that. And I want to save a little bit of time for looking at the package itself, which is shorter and simpler, of course. Test code is always longer and more complicated than the code it's testing. But we can see this other test. You know, if we think about it, what is this test? It's saying if you try to crawl a page where even that page's URL is not found, well, that's definitely a broken link, isn't it? But we can't crawl it to generate further links because it's 404. So that's testing part of the link checker, but it's not testing the part where you fetch the HTML page, you parse the links out of it, and then you go check those links. How could we do that? Well, we could use the same kind of structure, but we could create, what would we need to do? We'd need to make an HTTP request. We'd need to get an actual web page back that contains some links, or a link. We'd need to be able to call that link, and maybe its status not found. So now it's getting a little bit more complex, isn't it?
Yeah, 2 servers.
Yeah, but still understandable. So what we could have done is make one server which serves 2 different URLs, couldn't we? We could have said, oh, if it's, you know, if it's the root URL, serve this web page, or if it's the other URL, serve 404. But we didn't do that because we don't need to. We don't need to write any logic. We can just have 2 different servers. So here's the first one we're going to hit, which is why it's TS instead of TS2. We've set the called flag so that the test knows we got called. That's thing 1. Status okay, because it is okay. Here's your HTML. It's beautifully written. The one thing is, we don't actually know what the link will be because only the TLS server knows for sure, right? We can't tell it what URL to have. It will tell us. And it'll be 127.001 : some random port. So we ask the other TLS server, what is your URL? Okay, we'll template that into our HTML page. Here it is. So we've made that request. The web page has come back. Hopefully the link checker has parsed out this link. Now it's going to try and call that URL. Now we hit server 2. And we saw this already because it's the exact same 404 server that we had last time. Everybody reasonably happy with that?
Yeah, I'm just considering why you have the variable called for the 2 functions. Like, you're not going to know. Yeah, but okay, if the first one was called, the second one is going to be called too.
Yeah, that's right. So when we call server 1, we set called. So the test is going to check that. So if we never called server 1, we would detect that in the test because that would be a problem. We can't tell whether server 1 was called, but then, you know, the code just finished and it didn't go on to call server 2. But we will be able to catch that by virtue of the fact this won't show up as one of the broken links it detected, won't it? So it'll be like, you know, you could pass by doing nothing at all, except that we catch you out by checking the called flag. Or they both set called, so maybe we called one but not the other, but then we'll catch that situation because you won't have exactly the list of broken links that you should have.
But so you could remove the call from the TS2.
Yeah.
Okay.
And the rest is exactly the same, so that's fine. So I think we understand that. We'll move on to the next bit. So here it is, and you can see there's not very much here. So let's take a look. Adebayo, maybe, would you like to help us out here? Basically, what we need to do is just read exactly what the code says, and we'll try and work out why it says that.
Okay, all right. Good day, everyone. This is my first session.
Welcome aboard. Welcome to the basement lab.
Yeah, thank you. Okay, so I'm still very new in the game, but I'll just give it a shot.
Yeah, we're all learning together.
This defines the struct named checker with 3 fields or members.
Yeah, that's right. This is that mysterious struct that we saw in the test, isn't it?
Yeah, so we have the WG, which I think happens to be, will I say that's a struct in itself? Not too sure.
Yeah, I believe it is, yeah. Yeah, absolutely right. Anybody know what a weight group is? Or perhaps used one? Well, it answers the excellent question from before about how do we know when Go routines are done. So this is a nice mechanism that we get from the sync package, and the weight group sounds complicated, but is super simple. It's basically a number. So every time you start a Go routine, you increment that number by 1 to say, yep, I have 1 Go routine running. And the Go routine itself can call the weight group to say, okay, I'm done. So it will call wg.done, in fact. And that will decrease the number by 1. So what you can do is you can look at this number and say, well, how many is it? You know, if it's 5, that means I've got 5 Go routines running. When one of them exits, it will become 4, and so forth. And when it gets down to 0, I know they're all done. And we'll see how that works. So yeah, please continue.
Yeah, and then we have the HTTP client.
Yeah, we know what this is about, don't we? Because we just set that in the test.
And then there's the array, well, the slices, the slice for broken links.
Yeah, so we created our checker object here. We set the HTTP client to be the overly trusting HTTP client that trusts self-signed certs. And then we called the crawl page method on it, which we haven't got to yet. And then we looked at the broken links field to say, were the links that I was expecting in there? And that's just a slice of string. Very good. Please continue. What's next?
So we have a function, the new checker function, that returns a reference. Is that it?
Yeah, pointer to checker. That's
Checker,
right.
a pointer to checker, yes. So in the body of the function,
we're returning something.
Yeah, we're returning something. I'm trying to
Makes sense, doesn't
break
it?
that down to see if I can.
Yeah, let's break it down. So
I'm not sure I understand that.
Yeah, so we're returning. First of all, we're returning a checker, or we're creating a checker struct, and we're taking the address of it, and then we're returning that. So we're creating a new checker, creating a pointer to it, and then we're returning that pointer. That's reasonable, isn't it? But we're doing one more thing. We're setting its HTTP client. And what are we setting it to? We're setting it to an HTTP.client, which is the thing that you use to make HTTP requests. That's reasonable too, isn't it? Because we know we're going to have to do that. So that's absolutely fine, but we're doing one more thing. What we're doing is we're setting one of its fields. And we're setting specifically the timeout field, and you can probably guess what that does. We can have a stab at it anyway.
If nothing happens after the specified time, it closes the connection, is it?
Yeah, exactly right. How long will you wait for a web page to load in your browser? Probably about 10 seconds, right? If it hasn't loaded by that time, you'll just get fed up and close the tab. And that's exactly what this does. Why would we do that is an interesting question, isn't it? Why do we need a timeout here? Because we're not an impatient human looking at a web browser. Why do we need a timeout at all?
We don't want to hang on to compute resources indefinitely.
Yeah, I mean, one thing about this is, suppose we didn't have a timeout at all, that would mean by definition that the client will wait for HTTP requests forever. And that actually creates a vulnerability, doesn't it? Because if you ran a malicious server, you could say, okay, I'm going to write a server which accepts every connection you try to make and then just does nothing, holds the connection open, but never responds. And all of these Go programs with no timeouts would be sitting there waiting and starting more and more Go routines, leaking more and more resources, and eventually the whole internet would jam to a halt. So that would be pretty bad. And
the forever you said is not literal, right? You just meant a long time.
Actually, I don't know.
Because we have the kernel for max time to the TCP connection. So I don't know if it goes ignore that, but usually the kernel is going to drop the connection after the parameter in ccTL.
Right, that's interesting. So you're saying, you know, at the operating system level, there's going to be some limit on how long we can hold idle connections open. Yeah, that makes total sense. But as far as Go is concerned, its default HTTP client, which is the one you'll use if you call http.get, for example, has no timeout at all. And you could say maybe the standard library designers should have put a timeout, because we all know most people don't change defaults.
Yeah, and the defaults like it's huge, like it's 1 hour or something like that.
Right.
Yeah.
Well, I'm not that patient. I'm not a patient man in general. I'm certainly not that patient. So
just a quick question. You could use context, but since you're not passing these across multiple places, there is no need.
Yeah, that's right. So as we know from previous Code Club episodes, if we've watched them, we know that a context object is used to either cancel or time out a bunch of Go routines. And we might well want to do that with the link checker. You know, maybe the website is just so big that it's taking too long, and we just say, we want to cancel it. And in fact, because we're exiting the whole program, well, of course, that kills all our Go routines anyway. So it's not a big deal. But that's the CLI tool. Suppose we were running this as a web service. You could imagine, you know, checkoursite.com or something is a web service where you go and you type your URL in the box. It goes and spiders the site and checks the links for you. And now, because that server will be long running, we don't want it to leak Go routines, and we would like it to maybe be cancelable. So you're exactly right. We would probably use context for that. But we haven't yet. So just to, as a footnote to that, PSA, please set timeouts on your HTTP clients and servers, right? It's just the converse problem. If you have a server with no timeouts, then you're vulnerable to a malicious client who will DDoS you or just DOS you by opening a bunch of connections and holding them all open and never sending you anything. So there's a wonderful blog post from Cloudflare called "So You Want to Expose Go on the Internet." And it's basically all the lessons they learned about writing TLS servers and clients in Go at Cloudflare scale, right? Planetary scale. So they really know what they're talking about. And that blog post, which you can find, contains, you know, best practice, if you like, recommended settings for your TLS servers and clients. So it just gives you these. There's a whole bunch of other timeouts and settings as well, and also deprecating insecure ciphers in TLS 1.0 and things like this. But basically, if you're running a Go-powered TLS server on the internet, go and read that blog post, because it will save your company from getting on the 6 o'clock news.
Yeah. And by the way, you still need to show us the I/O multiplexing on the TP library. I won't forget.
Yeah, excellent. Good idea. Okay. How are we doing then? Can we look at crawl? We didn't actually call this from the test, did we? So what do we think crawl is about?
It's a method in the checker that receives a link as a string and calls crawl page, passing the link.
Yeah, and we know what that does because we saw it in the test, didn't we?
Yeah.
So that will recursively crawl a website that you give it.
Yep. And then it waits for the Go routines to finish.
Yeah, exactly. So when we were saying this wait group number will go up and down depending how many Go routines there are, and we don't know, of course, because we don't know how many links there are going to be on this site. You could say, suppose you had 100 URLs to check. You could start 100 Go routines, and they could all work concurrently. But we don't have that list yet. We will get it by crawling the site. So we don't know in advance how many links there will be. So we also don't know how many Go routines there will be. So what we want to say is just wait until that reaches 0. And it will reach 0 by virtue of each Go routine calling it to say, okay, I'm done, decrease your value by 1. And when they're all done, we will get to 0, and that's the end. So this is your entry point from the CLI, if you like. That it will crawl the page, and then it will wait until all the crawling is finished, and then it will return. And now here's the real thing. So this is basically the business end of the whole program. So who thinks they know what's happening here?
Okay, I can go. It's calling the function, the method get in the HTTP client library, passing the link and receiving a response and an error.
Yeah, and we know we could have just called http.get, which is the simplest way to make a request in Go. But if we'd done that, we would have been using the default HTTP client, which we've just been roundly abusing for not having timeouts. So that's why we use ours, isn't it? And there's one other reason, which is that when we're being called from the test, we can't use the default client because it doesn't trust dodgy TLS certificates, which the test servers will. So you're absolutely right. So we call the URL, we get an HTTP response object and an error. What's next?
So we check if error is not new.
Of course.
Or or the response code is not status okay, which is 200 code.
Right. Either way, it's broken, isn't it?
Yeah.
If it doesn't respond status okay, that's broken by definition. But also if we get an error, so when might we get a non-nil error from HTTP GET?
Bad request, maybe.
Yeah, exactly. So it doesn't, so not the HTTP status bad request, but if it couldn't make the request at all. So a good example might be invalid URL, for example.
Mm-hmm.
Maybe it's just, you know, doesn't contain a protocol, or, you know, it just contains invalid characters or something like that. So an error here would tell you, you didn't even get any of the letters in the URL right. So
Mm-hmm.
either way, it's a bad link, isn't it? That's what we're here to find out. So,
Yep.
So what do we do in that case?
So we add that link to the broken links, probably slices.
Yeah, that's this one, isn't it?
Yeah. So it's append the link into the broke links slice, and then it returns nothing because
we're done.
Yeah. And if there is no error or the HTTP code is 200, it's going to defer the response body close, which is a method, I would say, to close the connection.
Right, because that body is an IO reader.
Okay.
Indeed, an IO read closer. So that data is sitting around in memory somewhere, ready for us to start reading from it. And if we didn't do anything, it would stay in memory forever, and it would just waste memory. And if we waste a lot of response bodies, then we'll pretty soon run out of memory. So anytime we have some leakable resource, if you like a Go routine or a file handle or a response body, anything like that, the first thing we do after we know we successfully opened it is we defer closing it. That makes sure that however we exit this function, whether we call return inside some condition, whether we panic, whether we get to the end and exit, whatever happens, this will be called. So we're keeping Britain tidy, if you like.
So we call HTML query package on method parse and pass the body of the response.
Yeah, now this is a kick-ass library. Has anybody used this HTML query library?
No, I haven't used it, but I imagine what it does.
Yeah, well, here's the thing, right? Suppose you have an HTML page and you say, I want to get all the links out of that. How are you going to do that? Well, you could try to do string matching. You could say, I'm looking for a left angle bracket followed by an A, followed by a space and an href and something in quotes. And there's all sorts of different forms for that. And you might need to get down into very, very complicated regular expressions. And guess what? Your code would still not work because there'll be some dodgy HTML out there on the internet.
Yeah.
And if you're a web dev and you look at web pages in the wild, as it were, they are horrific. So, you know, there's two things you want to avoid at all costs as a programmer. One is date and time handling, of course. We all know that. The other one is parsing arbitrary HTML, because that is no fun whatsoever. So what our friend AntCHFX has done, to the great benefit of the Go community, is to write this library which you can just simply give it the response body, the reader, and it will turn it into some kind of structured document, in fact, a tree of HTML nodes. But you don't really need to know that as a user. You just say, in some way you have made sense of this random HTML or not. I mean, if not, then we'll get an error, but assuming you have successfully parsed it, we can now do some queries on that structured object, and we can use a query language called XPath to say, I don't know exactly what the syntax of this query is saying, but effectively it's extracting the URL attribute of all links in the document. And that's a very, very compact way to do that, isn't it?
Yeah. And then you finally iterate over all the reference you found, all the links you have found. and you call a method called inner text.
Yeah, now these things that we're getting back from find are not strings, if you like. That's what we want, but it's not giving us strings. It's giving us a slice of HTML nodes again. So again, it's, if you think of an HTML document as a tree, but any XML document is conceptually a tree of recursive nodes that contain nodes that contain nodes. And it's giving us a list of nodes, each of which we know because of the query is an anchor node, specifically the href attribute of the anchor node. Now, if we have that node, which is n, we would like to get the inner text, that is to say, the URL. So that's how we get it.
Okay. And then we increment the counter of Go routines running.
Yep, so this is the magic number which goes up and down to tell us how many Go routines we have, and the fact that we're adding one to it tells us we're about to start a Go routine. So something very cool is about to happen, and if you've never seen a Go routine before, hold on to your seats because you're about to see one.
And then you start a Go routine with anonymous function that do the same thing, like calls crawl page in the URL, and when it's done, it just call the method done to decrease the value and say that that Go routine is finished.
Yeah, very well said. So we've seen a function literal before because we saw one in the test. We passed one to the fake TLS server to be the handler. So that's perfectly straightforward. And we also call that function literal. And if we didn't have this keyword, then we would simply do this, right? But we would do it synchronously. So we would crawl page, we're calling ourselves. So it's recursive. So it's saying for all of the URLs that I found in that page, call crawl page for each one. And without concurrency, we'll just simply go deeper and deeper down this call stack, if you like. And eventually we will hopefully unwind it all the way back up, but we will have used a lot of time to do that.
If I want that, I would do in shell, a for loop.
Absolutely, or some lesser language like Java or C# or C++ or Rust. My YouTube views are falling away by the thousand with every extra language that I insult. But the point is, we have this magic keyword Go, which makes all the difference in the world, because what that says is, yes, call that function, but call it in the background, if you like, concurrently, and carry straight on. So as soon as we execute this Go statement, that function will start running somewhere else, if you like, conceptually, on some other CPU maybe, and our CPU is now free to keep looping over this list, which is super neat. So maybe we fetched 100 URLs, right? And we range over that list and we start 100 Go routines, one for each one. And then we're done. And all we have to do is wait for all the others to finish.
My only doubt is, should I care about like how many Go routine it's going to start? Let's say I have 1,000 links in my site, or 1 million links in my site.
Yeah, well, you've got a big website, obviously. I need to get you working on mine. Generate a bit of content for me. But yeah, the thing is, if you're used to working with concurrency in terms of threads, OS threads, you can do this in Python, and most languages have thread support, so that you can say, yeah, start another thread, and now leave it up to the OS to say, do I have any free CPUs that I can schedule this thread on? Maybe I do. Of course, you're competing with threads from other applications. But a thread is a comparatively very heavyweight thing. I mean, if you think about it, if you're swapping a CPU from one thread to another, that's a completely different process maybe. There's a huge amount of state involved with a thread, all of which has to be copied in memory. And so thread switching time is really slow. And you really don't want to ever switch threads unless you know you're going to be doing a ton of work on that new thread, What you don't want to do is to be thrashing back and forth, wasting more time with the thread paperwork, if you like, than you're actually doing anything useful. Go routines are very different. So they're sometimes called green threads because they don't trouble the OS at all. What they do is the Go runtime itself basically says, oh, I have a bunch of functions which I can swap around. In effect, the runtime says to the OS, give me a bunch of threads, as many as you can, and I will then figure out how to schedule functions to run on those threads. And what that means is, in an OS thread-based application, you can maybe run a few hundred threads, something like that, before your machine starts creaking. With Go, you can run 1 million Go routines if you want. I saw one of Francesc Campoy's videos where he does this, and he just says, yeah, let's, it's processing some big image, which is like 1,000 by 1,000 pixels. And he says, let's just start a Go routine for each pixel. And it's absolutely fine. So, cool. Yeah, I mean, you're right in the sense that this is potentially unbounded and we could end up with millions of Go routines, but it turns out that's perfectly okay. And if you pointed at a TripAdvisor or something, maybe some really big website where there's enough pages to cause problems, maybe it'll cause you problems. But I suspect what will probably happen is your program will just take a while to run, and maybe your laptop fans will start up. But it's all good. I mean, that's if you're running VS Code, then your fans are already at full blast all the time. So.
Yeah, I think it's my trauma as sysadmin, like troubleshooting context suite, speaking. Okay.
Right. But thank you. That was very good. So excellent summary. And I think we sort of have a sense of what's happening here, don't we? That even maybe we're not familiar with some of the concurrency details, and maybe we're new to things like wait groups. But at a gist level, do we feel like we get what's going on?
Oh, yeah. At least for me, it's pretty clear.
And it's a nice little program, isn't it? I think it demonstrates how easy it is in Go to do this kind of stuff, if you like. It didn't start out this neat. It was much longer when we started working on it, and we gradually got it smaller and smaller and smaller. Until we got it down
one question, John. I just wanted to understand if I'm understanding it. What I understood is right. This line number 43 will be executed the moment we reach the last URL on the page.
Yeah,
and then subsequently go backwards to remove one by one routine from the wait group.
That's right. So if you asked, what are these million Go routines? What is each Go routine doing? The answer is this. So it's crawling the page, and we know that crawl page itself can generate a bunch of new Go routines, right? Because we're looking at it. But for each Go routine, its job is just to call crawl page. When that returns, having maybe kicked off more Go routines or maybe not, but either way it's returned, we then call wg.done to say, please decrease the magic number by 1 because we're done. That number may be 1 million, so now it's 999,999. And all of the other things are doing the same thing. And as you say, when we get right down to the very last one, the wait group will be 1. And remember, in another Go routine, we're blocked here in this Go routine. We're waiting for this wait group to become 0. And after that, we exit. So here it's 1, let's say, and then we call wg.done. Now it's 0. We have exited. Now this Go routine exits, and that's the end of the whole program.
I see.
So that was the question we started out with, wasn't it? Is how do we know when we're all done? And now we know.
Nice.
Wonderful. Well, thank you very much to the panel. We're out of time, but it's been really fun. Thanks for joining me.
Thanks, John.
Thank you. Have a great weekend.
Yep. Hope to see you all next time. Bye-bye.
Thank you.
Bye.